Hello students, today we will see the difference between pressure and stress. Okay, because pressure and stress, if we see the formula mathematically, so both are defined as force upon area. So we will try to understand the difference between pressure and stress. Okay, so let us talk first about pressure. So generally in most of the books you can find it is defined as simple force upon area. But this is not the 100% correct definition for the pressure. Actually this force is not sufficient. Okay, so you need to write here normal force per unit area. Now the statement is 100% correct. Normal force per unit area is the pressure. I will make you understand by taking two examples. See here. Suppose I am taking here one block, okay, kept over a surface. Suppose I am applying some force. You can see this force is acting normal to this area. Let's say this force is of 10 Newton and the area of this surface is, let's say, 5 meter square. Here again I am taking the same block, okay. This time I am applying the force in inclined way, the same magnitude 10 Newton, and this time the angle of inclination of this force, let's say 30 degree with horizontal, okay. So if I will ask you find out the pressure in this case, so of course as per our definition normal force per unit area, and here force is normally acting, so you will simply put the value 10 upon how much area? 5. So you will get 2. And the SI unit of pressure is Pascal, so of course 2 Pascal. Very simple. Okay. Coming to this case, this force is not acting normally, so how to calculate the pressure? If you will calculate the pressure like this, same you are keeping force per unit area 5. Here also the area of the surface is 5 meter square. So this is the wrong way, because you are taking 10 Newton force, and you can see here this 10 Newton force is not acting normally, it's acting at some angle on the surface. Okay, so what will be the correct approach? Let us see. I am making this surface only, okay, and the force is acting like this at some angle, let's say 30 degree. So we will resolve this force into two components. One will be along this horizontal, one will be along vertical. Okay. So if this is 30, so this will become 30 degree, simple, and this force is 10 Newton. So this component will become 10 cos 30 degree, and this component will become 10 sin 30 degree. Okay. So now you decide out of these two components which one is perpendicular to this surface. Of course 10 sin 30 degree. So we will consider only this component of this force, that is 10 sin 30 degree. Okay, and what is the area given in the question? Is 5 meter square. I am simply making the surface only. Okay, so the value of pressure will be now equal to this normal force, that is 10 sin 30 upon area, which is 5 meter square. My dear, this will get cancelled, it will be 2. So 2 into, what is the value of sin 30? Sin 30 is equal to 1 by 2. So 2 and 2 will get cancelled, the answer will be 1 Pascal. Okay. So keep in mind force will be taken always normal to the surface. So this is about the pressure. Okay. Few more points we will discuss. Please see here. Pressure is a scalar quantity. What? A scalar quantity. Sir, how a scalar quantity? In formula of pressure, we have seen normal force per unit area, force is coming. So if force is coming, then it should be what? A scalar vector quantity. But it will be not the vector quantity, because pressure at a single point in any fluid has infinite direction. Just I am taking one example. Suppose this is a surface. This is a surface placed in fluid. Okay, placed in fluid, placed in fluid, placed in fluid. So over this surface, I am taking suppose one point here. Suppose force because of this fluid will act normal to this surface. Normal to this surface. Okay, this will be the direction of force. Okay, but the pressure at this point, will act from every direction. From every direction. You will learn this concept in the class in detail. That how pressure are acting from every direction. So you can see at the same point, this way, this way, this way, this way, this way, the same pressure is acting. Okay, so here we can see pressure has no specific direction. That's why pressure is what? A scalar quantity. Okay. Okay. So now let us see a stress. Let us see a stress. So we will discuss about a stress. A stress. As the name suggests, a stress. Okay, this is different than what we feel in our daily life, tension and stress. Okay, so my dear, I am taking one rod. Okay, and I am applying some force from both the side. Let's say F and F. Okay, so these two forces of same magnitude and opposite in direction are acting over this rod. So this rod will try to what? Elongate, but their molecules, the particles of this rod will oppose this external force. They will try to regain their shape and size. So right now, since forces are balanced, it means this rod is in equilibrium. Okay. So if I will cut some part of this rod, okay, and now if I will analyze, so you can see here, one force is acting F, but no force is acting here. This is externally applied force. And if the whole rod is in equilibrium, so this part must also be in equilibrium. So one force should come here. The magnitude should be equal to this external applied force to keep this part also in equilibrium. But who will generate that required force? Reaction. This will be generated by the particles inside the rod themselves. Okay, so this I am representing by R. So this R is what? Known as internal resisting force. So why you are saying as internal resisting force? Internal, because it's developed inside the rod, resisting. This reaction is resisting this external force. Yes or no? Okay. So now I will define a stress. So here I can write a stress is always defined as the ratio of internal resisting force divided upon area. So my dear, what what is internal resisting force? R. From where R is coming? It's developing inside the rod because of this elongated force. Okay. Upon area, which area? This cross-sectional area. Whatever area is having this, the same area will be here also. Yes or no? So this area A. But my dear, how you will measure this R? To measure this R, you have to go inside the rod and ask the particles that what force you are applying. But this is not possible practically. So mathematically you can see that this part is in equilibrium. So whatever will be the value of external applied force F, the same should be the value of this internal resisting force. So can I write this R is nothing but mathematically equal to F. So at this place of R, you can write the F upon A. Mathematically you can write a stress equal to external applied force upon area. But the reality is the definition comes from here, internal resisting force per unit area. Okay, don't forget this. Okay my dear. So here the rod is trying to elongate. Okay. So this stress developed inside the rod will be known as tensile stress and will be generally represented with positive sign. Okay. One more case I would like to take. Please see here. Again I am considering the rod. This time I am applying the force to compress the rod. Okay. Here we are trying to compress the rod. This F I am applying from externally. Okay. So again the particles of this rod will face problem. Yes or no? They will try to oppose these forces. How they will oppose? Let's see. So this part I am just drawing. Please see here. This force is applied from external and see this is in equilibrium. Why? Because both side force same. So this part must be also in equilibrium. So if this way you are applying the force, so one more reaction should come in opposite way, that is this way, and this is called R. Who will apply this R? The particles inside the rod. Okay. So again we can call this R as internal resisting force. Okay. So again here we can define the stress. Sigma is equal to internal resisting force, that is R upon area. This cross-sectional area, this will be similar to this. Okay, cross-sectional area. And mathematically, since this R is equal to F to keep this part in equilibrium, so at the place of R you can write F upon A. Listen my dear, although we are calculating the stress with external applied force per unit area, but it's defined only for internal resisting force per unit area. This is not so easy. Okay, we are having so many things to discuss upon this internal resisting force and this stress that we will discuss in detail in our class. Okay. So since here compression is coming, so this type of generated stress will be called as compressive stress and generally represented by negative sign. Okay. One more thing, my dear. Suppose one block I am taking and the lower end of this block is fixed. Okay. And I am applying external force parallel to the area. Which area, sir? This area. Okay, this area. Parallel to this area I am applying some force. So again here some stress will generate inside the body, and that stress is defined, represented with this sign, and is defined as this force Of course, because of this force, some internal force will generate, but mathematically that will be equal to this force alone. So you can write F upon A. This is shear stress. What? Shear stress. Shear stress. My dear, you can see in compressive and tensile stress, the external applied force was perpendicular to area. Suppose if this is the area, so either this way or either this way we were applying the force. That force is perpendicular to area. But in this case, suppose this is the area and we are applying the force along this way, that is parallel to the area. Okay. So now these three type of stress we have studied so far. Now we are able to compare the pressure and stress, my dear. Please see here. Now I am writing here pressure and here stress. Okay. So the very first thing, pressure is always defined as normal force upon area. And for pressure, force is applied from external. Okay. So this force is applied from external. External. But to define a stress, my dear, it is represented by sigma, always internal, resisting. Force you have to see, okay, upon area. So one big difference is this. While calculating pressure, force must be externally applied, and while calculating the stress, the force should be developed inside the body. Okay. The next difference is, my dear, pressure will be always compressive. Always compressive. But just we saw the things that stress can be tensile and compressive both. Tensile and compressive both. Yes or no? This is the second difference. Now, third difference, you can see, the third difference will be pressure is what? A scalar quantity. A scalar quantity. A stress is tensor quantity. What? Tensor. T-N-S-O-R. Tensor quantity. Now you will say, sir, we have not studied about the tensor. Actually, this concept is little bit different. All the scalar quantity, vector quantity, all the quantity derived from this tensor quantity. I will let you know how. Okay. So one major difference is this. Pressure is a scalar quantity and stress is tensor quantity. My dear, one more difference. In case of pressure, force applied must be normal. But just we have seen the case of shear stress where we were applying the force parallel to the area. So in case of a stress, that is shear stress, force applied is parallel to area. So these are the few differences between pressure and stress. Although mathematically formula is same, if we will talk about the SI unit, sir, tell me the SI unit. Of course, the SI unit of pressure is Pascal, or you can say Newton per meter square. And the same, the SI unit of stress is also Pascal or Newton per meter square. Yes or no? So this much differences is there in case of pressure and stress. Okay, my dear, just I will give you little introduction about tensor for now, and in the class, in my complete lecture, we will discuss the things in detail. Okay, so tensor is further classified as zero order tensor. Okay, the second one, first order tensor. The third part is second order tensor. Okay. So what is zero order tensor? Actually, for now, you just keep in your mind, there's a zero order tensor. Zero order tensor is called a scalar quantity. I will tell you how. And first order tensor quantity is known as vector quantity. And my dear, second order tensor quantity is given no name. Actually, the second order tensor quantity itself called tensor quantity or simple second order tensor quantity. So sir, can you give me the examples? Yes, of course. A scalar quantity, you know, mass, time, length, speed. Vector quantity, force, momentum, torque, angular momentum, like this. Then sir, what quantity will come under second order tensor quantity? So your stress, what? Stress, my dear. Stress, strain. What is strain? That you will define. And also elastic constants and area moment of inertia. Area moment of inertia. All these things comes under second order tensor quantity. Now, why scalar quantity is called G order tensor quantity? Because to define a scalar quantity, only magnitude is required, no any other parameter is required. And if you are defining any quantity, so magnitude must be there. That is the basic thing. Okay. So no any parameters need to define a scalar quantity except magnitude. That's why the scalar quantity is known as zero order tensor quantity. Now, for vector quantity, one parameter you need to define, that is direction. Along with magnitude, you need to specify the direction also. That is one parameter. That's why vector quantity is known as first order tensor quantity. Now coming to this, it's a second order tensor quantity means to define a stress, a strain or area moment of inertia along with their magnitude. You need to define two parameters. So one parameter will be direction, other parameter will be plane. So to define this quantity, you need direction and plane. That's why these are called second order tensor quantity. So right now, this is all for today's. In my class, we will discuss all these things in depth, in detail. Okay, and we will make our concept strong. Okay, so thank you.